Okay, this is lesson 84, and we're just talking more about multiplying radicals and also about functions. All right, multiplication of radicals. Remember that the product of the radicals is equal to the radical of the product. That is, that if m and n are non-negative real numbers, then the square root of m times the square root of n is equal to the square root of m times n. So if you're multiplying square roots, then you can just multiply the radicands. And if you have a product that is in a square root, like the square root of m times n, you can separate those two factors into two different square roots and multiply them. So the square root of m times n is equal to the square root of m times the square root of n. All right, so for example, if you have the square root of 3 times the square root of 2, that is equal to the square root of 3 times 2, which is the square root of 6. Or if you have the square root of 6, you can rewrite that as the square root of 3 times the square root of 2. So the product of the radicals, or the product of the square roots, is equal to the square root of the product. All right, so if you have something like 4 square root of 3 times 3 square root of 2, then you can use the commutative property of multiplication and rearrange all these things. This is all multiplication. 4 times the square root of 3 times 3 times the square root of 2. It's all multiplication, and in multiplication you can rearrange things any way you want to. So you could rewrite this. You don't have to rewrite it. You could do this in your head, but you can just rewrite this as 4 times 3 times the square root of 3 times the square root of 2. I wrote the exact same 4 factors. I just rearranged them, and I put the numbers first that are not square roots. So 4 times 3 is just 12. And then the square root of 3 times the square root of 2, which we just learned, is equal to the square root of 3 times 2. So that's the square root of 6. All right, so with multiplication, you're allowed to do that. With addition, you are not allowed to do it. Only with multiplication. All right, so again, over here, we've got 4 square root of 3 times 6 square root of 6. So we can rewrite that, if we want to rewrite it, as 4 times 6 times the square root of 3 times the square root of 6. I just rearranged those 4 factors. 4 times 6 is 24. And the square root of 3 times the square root of 6 is the square root of 18. All right, now that square root is reducible. Remember, we don't want to leave any perfect squares under the square root, any factors that are perfect squares. All right, so I could rewrite this as 24 times the square root of 3 times 3 times 2, because 18 can be written as 3 times 3 times 2. Now we remember that according to the definition of square root, the square root of a number times the square root of that same number is equal to that number. So for example, square root of 2 times the square root of 2 is 2. The square root of 3 times the square root of 3 is 3, and so on. All right, so I can see here on this right side of this equation that I have 24 times the square root of 3 times the square root of 3 times the square root of 2. And I just talked about the fact that the square root of 3 times the square root of 3 is 3. So I can rewrite this as 24 times 3 times the square root of 2. And 24 times 3 is going to be 72. So 72 square root of 2. So you have to make sure that you reduce all of your square roots. All right. Now we've got some problems that involve using the distributive property. So here I've got 4 square root of 3 times this sum, which means I have to multiply 4 square root of 3 times the first addend and then also times the second addend and add those two things. So 4 square root of 3 times 5 square root of 2, that's 4 square root of 3 times 5 square root of 2. So that's the first thing. And then I'm multiplying 4 square root of 3 times 6 square root of 3. So 4 square root of 3 times 6. Oops, I wrote that wrong. It wasn't square root of 6, it was square root of 3. Okay. So 4 square root of 3 times 6 square root of 3. All right, so I was just using the distributive property there. And now I'm going to use the commutative property to rearrange each of these add-ins. Or I can just actually do it without actually writing it. So this first term here, 4 times 5 times the square root of 3 times the square root of 2. I could write it down, rearrange it, but I'll just do that in my head. So 4 times 5 is 20. And then the square root of 3 times the square root of 2 is the square root of 6. Over here, 4 times 6 is 24. And then the square root of 3 times the square root of 3, remember, is 3. So I'm going to be multiplying that 24 by 3. All right, so I've got 20 times the square root of 6 plus 24 times 3 is 72. So that's all I can do with that problem. These are not, you can't add these together. You can only add square roots that are like square roots. So if I had 20 square root of 6 plus 72 square root of 6, I could say that's 92 square root of 6. But right now, these two terms are not like terms. We could say it that way. They can't be combined with addition. All right, let's look at the next one. Again, we're just going to use the distributive property. So 4 square root of 2 times 3 square root of 2 plus 4 square root of 2 times 5. So 4 square root of 2 times 5. First term here, 4 times 3 is 12. And then we're multiplying that by the square root of 2 times the square root of 2, which is 2. Anytime you multiply a square root by itself, you get whatever that number is under the radical, that radicand. So you've got 4 times 3, which is 12, and you're multiplying that by the square root of 2 times the square root of 2, which is 2. All right, the second term here, 4 times 5 is 20, and then you don't have any other square roots, you just have the square root of 2. All right, so the answer on this, 12 times 2 is 24, and then plus 20 times the square root of 2. We can't combine those two things. They are not like terms, so we're done with that problem. Okay, so functions. It's a little bit hard to grasp this mathematical idea of a function because we talk about it in so many different ways, all right? It's a concept, it's an idea, and we can represent it in lots of different ways. So one way that we talk about a function is to talk about it as a process through which we transform one number, x, into another number that we call y. Or as we sometimes call y in function notation, f of x. All right, y and f of x are the same thing. We take a number x and we do something to it. And when we're done, x has changed into another number, which we call f of x or y. All right, so you can kind of think of it as a machine that does something to numbers. So this function machine takes a number and then squares it and then adds 5 to it. So if you put 2 into the machine, you'll get 4 plus 5 or 9. So 2 is mapped to 9. 2 is a member of the domain, 9 is a member of the range. 4, if we put 4 into this function, square 4, you get 16. Add 5, you get 21. So 4 maps to the number 21 in this function. You could write these as coordinate pairs. 2 matches to 9, and 4 maps to 21. And then if you put 7 into this function, square 7, you get 49, plus 5 is 54. So 7 would map to 54, and you could write that coordinate pair. Okay, so You can look at a function this way as a mapping, matching certain numbers that are in the domain to certain numbers that are in the range. You can look at a function as just a set of coordinate pairs where the x's are your values in the domain and your y's are the values in the range. So the numbers, like I said, we put into the function. The x values are the elements of the domain of the function, and the numbers which come out of the function, or the f of x or the y values, are elements of the range of the function. Okay, so the big issue, the big thing that we want to remember about a function is that a function for every member of the domain, so every x, has to be paired with exactly one y. So every x can only have one possible y, all right? So if you look at these diagrams here that represent functions, you've got this first function. The domain is the first oval and the range is the second oval. The members of the domain are 4 and 2. The member of the range is 3, all right? So if you look at each x of this function, so 4, it's mapped to exactly one number, 3. Look at the next member of the domain. It also is mapped to exactly one number, and that's 3. So that is a function. If each member of the domain is mapped to exactly one member of the range, then it is a function. All right, look at this next diagram. Each member of the domain, look at each member. 4 is mapped to exactly one number, 3. 2 is mapped to exactly one number, 5. 1 is mapped to exactly one number, and that is 6. So each member of the domain is mapped to exactly one member of the range. That is a function. All right, let's look at this next one down here. Look at each member of your domain, 4. 4 is mapped to 3 and 5. That's not okay. 4, each member of the domain is supposed to be mapped to exactly one member of the range. This member of the domain, 4, is mapped to 2 different members of the range. So this is not a function. We would just call it a relation. All right, look at this relation over here. Look at each member of the domain. 4 is mapped to exactly one number, 3. That's good. 2, member of the domain, is mapped to exactly one member of the range. That's good. But look at 1. 1 is not mapped to anything in the range. That means there's a member of the domain that is not mapped to exactly one member of the range. It's not mapped to any members of the range. So this is not a function. In fact, it's not even a relation because there are members of the domain that don't have a match. All right? But the main thing to remember is that a function will be a relation so that each member of the domain is mapped to exactly one member of the range. All right? Another way to understand a function is just by looking at the ordered pairs x, y, which define the function. All right, so here you've got all these coordinate pairs, and these can represent a function. You don't have the equation, you don't have the graph, but you can look at the coordinate pairs and see what's going on here. And so to figure out whether this is a function or not, you need to look at each member of the range, each x, and make sure that it only maps to one possible member of the range, or one y. All right, right when you start out here, look at the first coordinate pair. X is 4, y is 3. So 4 is mapped to 3, exactly one member of the range. But wait a second, there's another coordinate pair here that has 4 mapped to -5. That means that this member of the domain, 4, is actually mapped to 2 different members of the range. It's mapped to 3 here and -5 there. That's not okay. So this is not a function. All right, so to make sure a list of ordered pairs is actually a function and not just a relation, we must make sure that no member of the domain is paired with more than one member of the range. Okay? That is the issue you have to deal with. Now, go back up here, before we leave this, go back up here and notice this is a function. It's okay if a member of the range has two different members of the domain. That's okay. The only thing that would be a problem is if there were a member of the domain that mapped to two different members of the range. So in this function, 4 only maps to one thing, 2 only maps to one thing. That's fine. That's a function. Here's the problem down here, where you have 4 mapping to two different members of the range. That is not a function, because that member of the domain has two different possible members of the range. Okay, so let's look at some more examples. Look at this first example here. Notice that every member of the domain is mapped to exactly one member of the range, so this is a function. Over here, y is mapped to exactly one member, p. A is mapped to exactly one member of the range, x, but m is mapped to two different members of the range. M goes with x and with 5. That's not okay, so not a function. Look at this one. Look at each member of the domain. A is mapped to exactly one member of the range. 4 is mapped to exactly one number of the range. That's 5. 7 is mapped to exactly one member of the range, so that is a function. That's perfectly fine. All right, look at the last one over here. It says your domain is all real numbers. Could be anything. All right? And the function is y equals x plus 2. So for every member in the domain, to get to a member of the range, you're going to add 2 to whatever that number is. All right? So this is definitely a function, because any number you put in there for x, you're going to get a unique value for y, just one. If you put in 3 for x, you'll get 5 for y. If you put in 10 for x, you'll get 12 for y. You'll only possibly get one possible answer. No matter what you put in for x, you get one unique possible answer. So that is a function. All right, let's look at these two sets of ordered pairs and see if they are functions. All right, so look at the first set. 4 goes with 6. That's fine. 7 goes with 2. That's good. 4, that's the same number as right here. It's now going with 5. So you have one member of the domain, 4, which matches to two different members of the range, 6 and 5. So if you were to draw a picture of this, you would have 4 and 7 in the domain, and then you would have 6, 2, and 5 in your range, and 4 maps to 6 and to 5, and 7 maps to 2. So when you have a member of the domain matching to two different members of the range, that is not a function. All right, look at this one. 4 maps to 8. That's okay. 15 maps to 6. That's fine. 11 maps to 7. That's all good. So that is a function. Okay, here's a few more examples. Which of the following sets of ordered pairs designate a function? All right, look at the first one. 1 maps to 2. 2 maps to 3. 3 maps to 4. 4 maps to 5. Each x has exactly one y, so that is a function. Look at B. 1 maps to 2, 2 maps to 3, 1 maps to 3. That means that 1, that member of the domain, is mapping to two different members of the range. So 1 maps to 2 and 3, so that's not okay. That's not a function. C. 4 maps to 3, 2 maps to 2, 4 maps to 3. Well, that's not different. 4 is just mapping to the same exact number, so that's fine. And 3 maps to 3. That's okay. So that is a function. Each member of the domain, each x, has exactly one y. D, you've got 1 mapping to -2, 4 maps to -1, -1 maps to -1, and 3 maps to -2. That's perfectly fine. You've got all these x values, and each one of them has exactly one y that goes with it. None of the x values have 2 different y's. So that's a function. All right, down here, you've got 7 maps to 11. That's good. 7 maps to exactly one member of the range, but 6 maps to 2 different members of the range. That's not okay, so not a function. Over here, this is not a function because 5 doesn't have anything matched to it. So it's not even a relation. It's not a function and not a relation.